I am Donna Young, and this presentation is for the National Science Olympiad Reach for the Stars event, Division B for 2017. The competition in 2017 is going to be held at Wright State University in Dayton, Ohio on May 19th and 20th. The event for 2017 for Reach for the Stars is exactly the same as it was for this year's competition in 2016, focusing in on stellar evolution, star formation regions, and supernova events. So this event, Reach for the Stars, and the astronomy event are both supported by the NASA Astrophysics Division via the Chandra X-ray Center in a partnership with the National Science Olympiad to produce these webinars, to produce materials and resources to help teams compete in Science Olympiad and the space science events, and also to attend coaches' clinics and invitationals. And the Chandra X-ray Center itself, observatory homepage, under the education menu is where this webinar is going to be posted. Every year we post 2 webinars, one for the astronomy event and one for the Reach for the Stars event, that are meant just to give a brief overview of the content and the resources to help prepare for the event. So when they are posted on the Chandra website, the webinar, there will also be a transcript posted for hearing impaired. And when they are posted, the PowerPoint that supports the webinar will be posted on the National Science Olympiad website. And there are notes attached to the PowerPoint slides for all of the deep sky objects with links directly to sites that will give the best general information on those deep sky objects to get the team started to learn about them for the competition. So those of you that competed in Reach for the Stars for 2016 this year, you're going to be really, really happy because there's hardly any changes. So you already have a big head start for competition for 2017. The event description exactly the same, an understanding and knowledge of basic stellar evolution, of the different wavelengths of the observations from all the different observatories through the entire spectrum, to look at the deep sky objects and the stars that are involved. And the event parameters are exactly the same. Each team may bring 2 8.5 by 11 inch two-sided pieces of paper with information from any source written on both sides of those 2 pieces of paper. If you are in a state that has a regional or a state competition that uses a planetarium as a venue, then you would need to bring with you a clipboard and a red light. The event is divided into 2 parts, as it usually is. The first part is the constellation and the star and the deep sky object identification. The second part is focused on stellar evolution, the electromagnetic spectrum, stellar classification, along with stellar properties such as temperature, radius, luminosity, including, of course, the magnitude and luminosity scales, and the distance modulus and inverse square law. So for part 1, for the constellation, star, and deep sky objects, the only difference for 2017 from 2016 is that one of the constellations, Monoceros, is no longer there. However, it has been substituted by 2 other constellations, Serpens and Tucana. There are 5 deep sky objects on this list that weren't on there last year. Gemini, Gemenga in Gemini, the Ring Nebula in Lyra, the Eagle Nebula in Serpens, T Tauri in Taurus, and the Small Magellanic Cloud in Tucana. So as you can see, we have the constellations listed. The bolded stars are major stars within those constellations, and everything else are the deep sky objects that you are required to be knowledgeable about for this upcoming competitive year. If you group those different deep sky objects into related groups, we have star formation regions. There are 8 of those. There are 4 supernovas, 5 specific evolutionary stages, and 3 galactic objects. One is the black hole at the center of the Milky Way galaxy, Sagittarius A, and then there is the large and the small Magellanic clouds that are in the southern hemisphere. The 5 evolutionary stages, there are 2 planetary nebula with white dwarfs, there's 1 black hole, there's 1 pulsar, and there is a protostar. And we'll go over those a little bit, as you know, as we go along. The same 4 supernovas were on here last year. Cassia and the Crab are type 2 core collapse supernova events. And then we have Tycho and Kepler, and those are type 1a events, the thermonuclear destruction of white dwarfs. So this graphic that if any of you have been part of Science Olympiad for any length of time at all, have seen this over and over again because it's a pretty graphic to illustrate the story of stellar evolution. Now, the sequences on this graphic that we are going to be concentrating on this year, not the 2 bottom ones, the brown dwarfs and the red dwarfs, because they're pretty boring. They just sit there and radiate away for trillions of years and just turn off. We start with the sequence that has the sun-like star on it. We have stellar nursery, which is part of a big stellar complex region. It has clouds of gas and dust that collapse into small little clumps. Those clumps get more compact, they accrete more material. It gets hotter and hotter in the center of that core of gas and dust. When it becomes hot enough for hydrogen to start fusing into helium, then we have a star. And when the star is formed, it has a specific amount of mass, and the mass that it has when fusion starts dictates what is going to happen to that star through its entire evolutionary sequence until the final demise of the star. So, and the more massive the star, the shorter the lifespan. So we are concentrating on sort of sun-sized stars that evolve, as you can see on this graphic, through the red giant stage, become a planetary nebula and a white dwarf, leaving the white dwarf behind. More massive stars will go through a type 2 supernova core collapse, leaving behind a neutron star or some flavor of a neutron star like a pulsar or a magnetar, and then a more massive star which will collapse into a black hole. That's the part of the stellar evolutionary history of stars that we're concentrating on again this year. When fusion stabilizes, hydrogen to helium fusion stabilizes, and you have a real star, it is now called a main sequence star. So instead of looking now at this pretty graphic and this second line of curved stars, which actually represents the main sequence, now we're going to look at it in a more scientific way, the HR diagram. So, and I will go over this a little bit further along in this presentation, but I'm going to be using HR diagram terminology, so I just want to go through the terminology a little bit and make you a little bit familiar with the HR diagram, which is basically a plot of 2 stellar properties, temperature and absolute magnitude. You will see at the top that there is temperature that starts on the left-hand side with 30,000 Kelvin and moves horizontally to the right-hand side of the HR diagram where it says 3,000 Kelvin. Underneath it at the bottom, you will see stellar class, OBAFGKM. The stellar class is derived by the temperature of the star. So you will see HR diagrams that will have temperature and absolute magnitude. You will see some that have luminosity and spectral class. You will see some that have absolute magnitude and spectral class. You'll see all different kinds. This one happens to have all 4 of them. temperature, spectral class, absolute magnitude, and luminosity. So the absolute magnitude of star is how bright it actually is. Its intrinsic brightness, which is not dependent upon its distance from us. So if you know the absolute magnitude of a star and its temperature, you plot it on the HR diagram, and where it ends up on that HR diagram tells you what phase of its evolutionary history it is in. It is actually a plot of stellar evolution. So the absolute magnitude, again, is how bright a star really is. If you took every single star in the sky, lined them all up the exact same distance from the Earth, you would know which one actually is the brightest and which ones actually are the dimmest, because you take out the factor of distance, which we cannot determine how far away something is from our perspective here on Earth. Luminosity is a relative scale. It is simply, we call the sun one solar luminosity, and then other stars are either more luminous, 10 times, 1,000 times, 100,000 times more luminous than the sun, or less luminous, 1/10, 100th, 1,000th as luminous as the sun. So there is a specific relationship between luminosity and absolute magnitude. If you know the luminosity, you can determine the absolute magnitude. The sun is sitting right about here, because it is obviously luminosity 1. So if you go to the luminosity scale where it says 1, you go over to the main sequence and keep going to the other side, absolute magnitude, it says +5. So our sun is a G class classification, around 6,000 K, temperature, 1 solar luminosity, 5 +5 absolute magnitude star. The magnitude scale is a logarithmic scale, so it goes from 0 up to, this particular graph only goes to -10. So the larger the negative number, the brighter the star, and the larger the positive number, the dimmer the star. So the actual stars that have hydrogen to helium fusion taking place in their core, which has stabilized the star, so the radiation pressure from the fusion process out is counterbalancing gravity, which is always trying to collapse a star. So pressure out, radiation pressure out, gravity in, we have a, quote, stable star. We call it a main sequence star. Once a star starts to evolve, it can evolve from the main sequence up to the red giant branch, or it can, more massive stars evolve horizontally across to the supergiant branch. So you will see, unlike most mathematical graphs that have 0 at their origin, this one is just reversed. At the origin is where the hottest is. So all of the stars are in the upper left-hand corner of the HR diagram are the brightest and the hottest. On the upper right-hand quadrant of the HI diagram, then you have the brightest and the coolest. At the lower left-hand quadrant of the HR diagram, you have the hottest and the dimmest, and on the right-hand bottom corner, you have the dimmest and the coolest. Stars also have a luminosity class, and it goes from the supergiants are luminosity 1, and then the next step down is luminosity 2. The red giant branch is luminosity class 3. All stars in the main sequence are luminosity class 5, and there are stages in between as the subgiant branch, which are stars that are evolving from the main sequence to the red giant branch. They're sort of halfway in between. That's luminosity class 4.